I'm going to try to graph it myself. So let's see here. The circle, no. Oh, gosh, I'm so sorry. The circle should be 3 sine theta. That's a typo. Like, sine 3 theta is a 3-petaled rose. Sorry, that's a total typo. So let's, r equals 3 sine theta. There we go. Now it's going to be a circle, whereas before it was not a circle at all. It sure does.
I don't understand.
Why is it so thick?
Dang, Shotty, she's big.
Oh, it's because I wasn't radiant.
Got to be in radian mode, yep.
Yeah, we were all in degrees because of AP Physics yesterday.
We're supposed to be in
So
radian.
then for my theta max, is it just 2 pi? My window?
Isn't it?
Wait, are we in degree?
I think, let's see here. So for the cardioid, you're going to need 0 to 2 pi. For the circle, I think you can actually get away with just 0 to pi.
So what do I do for my window?
I do 0 to 2 pi.
What should I do for my step?
Oh, I don't know, like 0.1 or something?
0.1? Is that 7.5?
Oh, that's pretty weird. You're going to get a weird looking graph. I think it looks like this. Am I right?
I got something exact.
Decent? Okay. Okay, so this says find the area both inside the circle and inside the cardioid. So let's define the area that we're talking about. Wouldn't this area be this yellow area? You see how that is inside the circle and inside the cardioid?
Yes.
Let me illustrate by using red what's not. Like this little part down here, that's not in the circle and in the cardioid. That's in the cardioid, but it's not inside the circle. Does that make sense? The red part, do you see that? It makes sense, Aiden? Okay. And do you see how this is also similarly in the cardioid but not in the circle? So the red area wouldn't work. And then isn't all of this up here inside the circle but not inside the cardioid?
There is.
So only the yellow is what we want. I want to remind you from yesterday, area with polar is not a summing of rectangles. It's more like the weather person on the news, their little radar that sweeps across a shape. And as we sweep across the shape, the radial line will get longer or shorter, whatever it needs to do. Any ideas? Any ideas? Let me ask you this. Any ideas on what you think might be important that we don't know yet?
The intersections.
The intersections.
Oh.
Yes. So right here,
I wasn't.
and of course on the other side there's a similar looking intersection point. Those intersections are quite important. How do you think we could set the r's equal? There you go. Perfect. Okay, so if I do that, I get 3 sine of theta is equal to 1 plus sine of theta. So with this, I would get 2 sine of theta equals 1. Sine of theta is equal to 1/2. Therefore, we should get 2 angles out for this, right? There we go.
We got it.
And you can actually, the picture is well drawn enough where you can see that that's fairly realistic, both based on the math and the picture. So I think what I'm going to do here, I'm going to attempt this. I'm going to attempt to draw in a radial line representing that. My radial line is going to be green. So for that angle, is that visible? Yes, it is. Can you see it? So that little green line represents the angle where the 2 curves intersect. And do you notice anything? I'm really happy the way that turned out. You notice anything about this? Say again? Okay.
What are you asking?
Do you see anything? Does anything like unique jump out to you as far as how that green line is drawn in there, and the area we're trying to find, and the way the curves are interacting? Is a strategy emerging at all?
So I did from pi over 6 to 5 pi over 6, that's only the cardioid.
Okay, let's go there. Let's go there. So what Santi just said is from pi over 6, which is the green line, to 5 pi over 6, and I'll draw in a couple of blue radial lines to represent this domain that Santi's talking about. For that whole domain, isn't the cardioid, the graph, telling the radial line how long to be? And I get over here to this other end, and I'm going to make that a green line. So along that whole domain, pi over 6 to 5 pi over 6, it's the cardioid that's essentially determining area, right? What about the rest? Because he said on that domain, is there other parts of this domain?
The rest of the circle.
Yeah. So you go from 0 to pi over 6, and then another one from 5 pi over 6 to pi.
Yes.
Of the circle.
And isn't Logan referring to like this tiny sliver of area that I almost cover up with my arrow?
My God,
And then this other one, this other little itty bitty sliver of area. For those two little tiny slivers of area, isn't that where instead of the cardioid telling the radial line how long to be, this time it's the circle? So this is really hard to draw. So Nick, let me just show you on my screen. Okay. So from green line to green line, it's
Is that
the
pi
cardioid.
over 6 to 5 pi over 6?
Pi over 6 to 5 pi over. So this domain, which is pi over 6 to 5 pi over 6, it's the cardioid that's saying radial line, this is how long you get to be. But do you see this little tiny sliver? In fact, we could try to color it, I suppose. This little red sliver of area there, and this other little red sliver of area there.
Is
For
that
both
dictated?
of those, it's no longer the cardioid that's determining the end of the radial line. It's the circle. Do you see how the gray circle there is defining the end of all those? And I can't even really draw on those little radial lines because it's such a small area. But it's the circle that's telling the radial line how long to be.
And is that from 0 to pi over 6?
Yeah.
And then like 5 pi over 6 to 2, or pi?
5 pi over 6 to pi. Yes.
Could you just do from 5 pi over 6 to 2 pi?
Whoa, hold on. Could you
Oh, no, you couldn't.
Could you just do it
Like, could you just
from 5?
like take the integral from 5 pi over 6 to 2 pi of the circle? Or no?
Whoa.
Oh.
I'm trying to picture what that. So the circle, really, honestly, the circle's domain is just 0 to pi. Like you can draw the whole circle in 0 to pi. Try it.
How do you know that? Just like,
So where I'm coming from there is,
wait, I think I understand.
I'm thinking of radial lines here. So
I think I get
and
it.
ignore the cardioid. So I've got a gray radial line. So the gray radial line, when it's pointed straight right, and I'm just thinking about the circle here, isn't the circle radius 0?
Right.
And then I can sweep out the whole circle. I got half the circle made in pi over 2,
Right. Okay, that makes sense.
and then I got the whole rest of the circle made by the time I get to pi. That is not true of the cardioid, but it is true of the circle. The cardioid, like these two little, the parts that I'm highlighting in orange, those two little parts down below, that's where you need the pi to 2 pi
Mm-hmm.
to get. I know that they're very small, but I need that full pi to 2 pi to get those. Okay, so yeah, Sam.
Wait, so we usually do 5 pi over 6 to 7 pi over 6 to find both of those areas?
Man, be so careful. So
Who said that?
I don't think I would. I don't think there's any need to. When you say both of those, you're talking about the two little tiny slivers of area. I don't think I'm going to do 7. I really got to think about that. I think there's a much easier approach. Than like there's. I just don't see any need to like delve down into the third quadrant for the circle, right? If you're thinking symmetry, which I think would be a wise thing, there's a way easier way than like going down there and saying, well, gosh, there's no circle down there, so that means the radius negative, and does that make sense? Because if you think like, so sine, so let's say sine of pi over 4 is, you know, like this, and, or sine of, I guess it would be 5 pi over 4 would be that. And so you'd get negative root 2 over 2, which would actually put you backwards back into the first quadrant. So I think that's where it's coming from. But if you don't have to mess with that, why mess with that? That's what I'm thinking. Hey, can I make a suggestion? Here is a possible way to do this. What if I did the integral from 0 to pi over 6? You know, it's 1/2, and I got the circle in here. Wouldn't that integral right there, 1/2 integral r squared for that domain of the circle, wouldn't that get me, how do I want to do this? This will get me, I'm going to do this in dark green. Wouldn't that get me this dark green little tiny sliver of area? You with me? Okay. Plus, what if I did 1/2 integral from pi over 6 to pi over 2 of the cardioid squared? Wouldn't that get me this other green area, which I'll just sort of shade like this? And then take the answer to that. You said it, Aiden. And double it. Meg, you with me? Are you way ahead of me?
Yeah, I already have it.
Did you have something like that?
I have.
Oh, I see what you did.
Well, I did
That's
it
fine.
differently, but like I understand it differently.
So you,
I did it like I have it differently.
well, tell us how you did it. I'm curious.
I just have like what we were talking about before, like 0 to pi over 6 of the circle part.
Okay, so 0 to pi over 6 of the circle. And make sure you guys are writing 1/2 r squared there. So there's the circle part.
And then the other side too is 5 pi over 6 to pi.
Okay, so 5 pi over 6
Of
to
sine,
pi of the circle still.
Yeah, 3 sine of theta.
Okay,
And then like the part inside of the cardioid in the circle. So
and what would that look like?
1/2 integral from pi over 6 to 5 pi over 6 of
There we go. Lovely.
1 plus sine of theta squared.
Got it. That would work just fine. Perfect. So that's just like going little piece plus big piece plus other little piece gets me the whole thing. Cool. What I did is I said little piece plus half the big piece times 2 gives me the whole thing. And so just like we did yesterday, there's got to be multiple ways we could approach this. There's 2 of them up there. I think they would both work fine. Clearly, I hope it's clear at this point, we would just use Math 9, right? So for me, the main issue is the setup. The secondary issue is making sure you're in rating mode, making sure your fingers hit all the right buttons.
We'll always have either the graph or be able to graph the equations if we're given a problem like this, right?
Yeah, for sure.
Okay, cool.
And yeah, and a lot of these would probably just say, write an expression for the area.
Yeah.
It wouldn't even say, what is the area, right? So we would just stop right there. So, okay. Doing okay? All right, so there's a couple more. We'll get into some interesting things here. So check out number 3. Number 3, yes, this is such a good one. So this is right off of an AP test. This is 2003 BC3. It is definitely calculator active. So part A just says, the 2 key words in part A really are show that. So we're supposed to prove something. We're supposed to prove that that polar curve could be rewritten as from the rectangular form over to the polar form. And then B is more like what we've been talking about. B is an integral expression for the area of that region. So,
Easy.
have at it.
Okay.
common for there to be a polar question on the free response. It doesn't happen every single year, but it does happen fairly frequently. You guys all mostly started on A, or did you decide to start on B?
A is not that bad.
A isn't, yeah. If you can get the conversion set up right, it's like pretty straightforward.
You see it really quickly.
I agree.
Real quick, it says use the polar equation given in part C.
Part C.
Oh.
There's no part C.
It should be part A. Sorry. You can see I kind of skeletonized this one.
No problem.
Yeah, so polar equation of part A. So that would be the thing that you basically just proved is actually true in part A.
Yeah.
Yeah, for sure.
That's R percent theta squared. R squared.
See again? Oh, really? So you fixed.
Well, how do you get
And then
X
you do like,
equals
well, X equals R percent theta, and then you just do. Is it R
When you're talking about how to,
You need to like this, right?
into an angle essentially, right?
Yeah.
Because it looks like you're saying, hey, the integral is from 0 to, I'm not sure where.
Yeah, it's anything like intersects.
Yeah, so it goes up to that, so you, so like we're sweeping out area from here up to there, right?
Yeah.
So just going right up to there. So we're trying to figure out that angle. This might help, like if I just made this a little triangle. This is written a little weird. What's the slope of this line? 3/5, that's right. So this would be 3, and then this whole base would be 5, and that's the angle we want, right? So,
you just do it the
So the slope is 5/3, right? And-
Slope is 3/5 actually, because it's written x in terms of y instead of y in terms of x.
Oh, okay, I got you.
Which I don't know why they did it that way. There's probably a good reason, but I don't know why.
I'll have to be careful of that next
So
time.
can you use your calculator to find the angle at?
You can. I don't think you have to. Knowing how, like with these free response questions, you can write like as long as the number you wrote is equivalent, you can just write an expression for it. So
like inverse tan of 3/5.
right. So you could use your calculator to figure out roughly what that is, the 3 decimals. You want to take it to 3 decimals, or you can just do that.
Just leave it as is.
Okay, we'll take a few more minutes here to try to get to a good spot with this one. I think the proof in A will be pretty quick, and then hopefully you're finding that B, even though it's maybe a little uncomfortable, B isn't too bad. All you have to do is set up the expression. You don't have to even use your calculator to evaluate it.
Well, I just don't. I don't know.
That's just fine.
I found the angle.
Bless you.
It doesn't go around the origin. That's my issue.
See?
The circle is not like following the origin.
We're trying to find the area of S.
Right, but like if the
S
circle
does
was like
like
this way, then you could just do the angle from 0 to this angle of the circle.
So what we're doing here, they want us to find area of S.
Right.
So, like with the end of your pencil right there at the origin, we just need to sweep out and rotate. Up to here, we just need to sweep out those sectors. So like your first sector. Like that, there's your second sector. So on and so forth, right?
But how do you like, just because the circle's like, it's like curved the other direction.
That doesn't matter.
So I just don't know how you, because then if you find the.
What is, so the radial lines start at the origin of the pole, and they go out here. What is telling those radial lines how long to be?
The circle.
It's hyperbola, but is it hyperbola? Yeah, it's hyperbola.
Maybe, whatever, I assumed it was a circle.
It's hyperbola, but regardless,
Whatever.
we're not. I feel like you're
The thing.
fixated on trying to find this area,
That's where I was confused.
and it's not asking us to do this. It's find the area of S.
I just didn't know how to use this to find that.
I think you should be using polar, not that.
Well, I mean, like, I was like.
Oh, wait, I know.
Like, so I just use like angle from 0 to,
It's not.
like, I just did,
I don't need to.
whatever.
Oh, shoot. I think
Look how this is big. This 3/5 of.
Wait, what's yours? What'd you get?
Does that work?
As long as you have a 1/2 out front, yeah. That's it, because it's 1/2
Because you gotta subtract.
r squared.
No, you don't.
d theta.
Because what that line gives you.
That's it. So like this r is simply the expression for how long the radial lines are. Radial lines go from here up there to the curve. But we're not trying to find this, that'd be a whole other ball.
Yeah, I know, but you have to eliminate that area
We're trying
either
to
way.
find this
No,
area
you don't.
here.
Because
No,
I
that's
think
where
that's
it's stopping.
No, that's where it's stopping.
It felt like you were concerned about this area.
Yeah.
I know,
Well,
that's
we
what
don't
I'm
need-
saying.
Yeah.
So you don't have to eliminate anything.
Yeah, we're good. I got it.
Okay.
This is just area S.
All right, let's do this.
I know, but
Hey, can I show you guys A real quick? Let's just make sure we're on the same page with A. A is a substitution. You start off with x squared minus y squared equals 1. And we know that x is equal to r cosine theta, and y is equal to r sine theta. So this would be r cosine theta quantity squared minus r sine theta quantity squared equals 1. This gets me to r squared cosine squared theta minus r squared sine squared theta equals 1. Then it's a factoring out of the common factor. Once you factored out the common factor, it becomes fairly obvious that just a division on both sides will get you to where you want to go. So really this was, I would say that A was trying to assess, do you know how to convert between polar and rectangular? To me, that's really the point of that question. Because beyond that, it's some pretty simple algebra. Okay, and then part B, we are concerning ourselves with finding the area of S. And if you wanted to think about it like those sectors we talked about the other day, a couple of representative sectors could look like this. Something like that, I don't know. That last one doesn't look very good. We'll just go with that. And so, obviously, when we're trying to find the actual exact area, we want the number of those sectors to head towards infinity, therefore making them very, very skinny and very unsector-like, right? Basically just like line segments. And so then, how am I going to use that? Hopefully I know that the area formula for polar area is 1/2 integral of r squared d theta measured from alpha to beta. So we would maybe say area equals 1/2. And I don't know what's easier. I guess maybe the easiest part is that the alpha is 0. Right? I'm going to start sweeping area when I'm facing straight, right, and come on, computer, you can do it. Anyways, I'm going to be facing straight right, and then I'll sweep across this like so. So 0 makes sense. Maybe the next thing that would be easiest would be where the angle where I stop, right, the beta. So the key to that is seeing this x equals 5/3 y. This means that the slope of the line could be seen more clearly here. Therefore, slope is 3/5. And so, frankly, you could use like a triangle, or you could remember that dy dx just equals the inverse tangent of, or excuse me, dy dx equals the tangent of theta.
Yeah.
And you could just use that relationship. I would be totally fine. In fact, I'd be overjoyed if you just wrote inverse tangent of 3/5 right there. I think that would be great. If you used your calculator and found out, I don't know what it is, 0.8 or something like that. Oh, it's 0.54? Okay. Whatever. Oh, yeah, it's less. Never mind. In any case, that would be fine too. Just make sure you're accurate to 3 decimals if you did something like that, or you could just write it like that. And then here's the best part. It might be really mystifying to think, oh my gosh, it's supposed to be r squared, and what is that? Keep in mind, you have r squared for that curve. Like in part A, you proved that that is r squared. And so, to be honest, all you really need to write here is what you proved in part A, d theta. Like that itself is r squared. The real trap here would be to put that in parentheses and square it, right? Thinking that it's r, but it's really already r squared, so there's no reason to square that, and you'd be all done. What do y'all think? I talked to several of you as I was walking around. Do you have any questions? Logan.
So we're finding the area of S, right?
Finding the area of S.
Which is bounded by the one line.
2 lines, really, the x-axis and the line. So yeah, so the boundaries for sure. Yeah, the boundaries are, orange is probably a bad choice, but that line, and then the red curve on the end.
It's also bounded by C, so why wouldn't we account for that? Why didn't we account for that?
We did. That's the R. Right? So,
Okay, so why didn't we account for like your...
I know when I was talking to Santi, he was getting kind of concerned about this area.
Yeah, that's what I'm concerned about.
And it's almost like you're thinking rectangularly. You're thinking, oh, I need to do like integral of like the higher curve minus the lower curve.
Well, I found the polar equation of the straight line, and then
Sure.
I subtracted the other integral from it.
You're thinking very rectangularly.
Okay.
I want you to think like the weather radar map. All we're doing is we are accumulating area by sweeping through, by doing this.
Yeah.
So I am just taking a sector area, like those little sector areas, and I am sweeping across this region.
So
I'm not subtracting anything. I'm not adding anything. I'm just saying, hey, what's the area of this little sector? Okay. What's the area of that little sector? Etc. all the way across. I'm not subtracting something from something else.
Right, because I was just thinking, like, if we did just the integral of the curve C, wouldn't we be finding the area outside that because the...
Okay, now here's the question. Are you doing it in a rectangular format or a polar format?
Doing it in polar.
Okay, so if you did the area of curve C, so if you set it up as integral from, we haven't decided from where to where yet. If you're doing it in polar form, doesn't it have to be 1/2 integral of something squared?
Mm-hmm.
Okay, so it's that. If I did 0, and maybe I didn't do the inverse tangent pi over 3, maybe I did like pi over 3 or something. All that would just be a much larger area. So if I did something like that, it would be all this area.
Mm-hmm.
If I'm looking for this purpley area out here,
Yeah.
I'm going to have to do it in rectangular form. I'm going to have to use that x squared minus y squared equals 1, and I'm going to have to use rectangles
Okay.
to get there. Now, actually, no, I take that back. That's not the only way to do it. Check this out. If I really wanted the purple area, I could make a triangle, and I could just use geometry to find the area of the triangle,
Mm-hmm.
and then find the green area with polar, and then subtract the green area from the triangular area. That would give me the purple area. So I could either fully buy in with rectangular and just use rectangles, or I could do the thing that I just said.
Okay. So you're not really finding the area under a curve when you're doing polar.
No. Well, not in the classic sense, no.
Okay.
You're finding let me put it like this. I'll put it like this. This might help, Logan. Instead of thinking I'm finding the area under a curve, think about I'm finding the area between this radial line and that radial line.
Okay.
Does that make sense? That
Yeah.
help? Yeah, it's not,
So,
when you say under, it like immediately brings to mind rectangles, doesn't it?
yeah.
So think of it as I'm finding the area between this radial line and that one. Whatever's happening out here curve-wise, I don't know, but I'm just finding what's the area from here to here. Okay. Alrighty. Great questions. These are very, very good. Okay, so this next one is definitely calculator active. This is from 2005, and I think this is the full AP question. I'm glad that you have the page in front of you because this is kind of,
When is our quiz?
I don't know, look at the calendar. It's not tomorrow.
It's the 29th, and it's either the 29th or the 30th.
It's a ways, yeah.
Because I know that I have to make it up.
That's right. I'm not rushing you through this. The two websites are actually in there. It's 10.4 and 10.5, and then we talked about that.
That's what I was doing there.
They're due a ways off because like this is new and like you guys are doing pretty well with this, but I want you to have time to like really get it. So
Well, we're done working on it after today, right?
today is the last like new day of polar. Yeah, we'll finish this one, and this is really all we need to do.
So are we gonna like review it all before our quiz?
We're gonna roll through series.
So the rest of the time is like kind of just for us to on our own deal with that.
Yeah, or you can come in, whatever. But we don't have class time to just. Honest to God, I wish we had like another week to just say let's just practice polar for a whole week in class.
Yeah.
I wanted to do the hyperbolic trig.
Oh yeah, hyperbolic trig functions. Yeah,
Interesting. I don't even know.
they are.
That is a weird love.
Yep, they're based on. It's really kind of crazy how it all works. Based on e's essentially, different combinations of e's, but then the derivatives behave in kind of a way like similar to sines and cosines. Yeah, it's very interesting. It is. Hey, so I'm hoping that A looks like something that you would say, wow, this is exactly what we've been covering the last day or two. And then B, C, and D are a little more of, I would say, more review style questions. This is definitely calculator active.
Why is it so lumpy on?
Oh, because I drew it by hand.
Oh,
Oh,
you
okay.
drew it.
Yeah, this is,
I was like,
I
what's
drew this out a
wrong?
long time ago. This is like before Desmos was a thing, and I just haven't replaced it with a lovely Desmos graph. I probably should.
Disappointing, Mr. Anderson.
I am sorry.
That's okay.
You can use your lunchtime and do all the Desmos graphs you want. Have fun.
Alright, was your right?
Sure, Anderson.
Yes, sir.
Is this coordinate -2 or coordinate 2?
X coordinate -2. -2. Yes.
Well, graph it again.
So we're going to kind of work through this piece by piece. So please try A. Says find the area bounded by the curve and the x-axis. It's calculator active, so you could use your calculator to figure out what the domain should be.
That's so nice of them. They gave us
yeah.
the derivative.
This is sort of a cardioid-ish like thing. It's like part of a sort of a cardioid. It's not really a cardioid, but it's got that kind of pointy part in there.
It's theta plus sine theta.
Oh, I did 2 signs.
Yeah. It's a weird graph. Okay. How do you find
Sure, Anderson.
Yeah.
The second one? If you just multiply the r times cosine theta and solve for theta, then set that equal to -2, does that work?
Yes.
Is that how you, but then how do I like put that in the calculator?
You're off to a good start. You're
Is
off to a
the
good start.
first one not asking
Hey, let's talk about the first one. Again, I'll try to illustrate. As I'm finding area, the area that I'm finding is basically represented by, I'll try to represent with some radial lines. I'm sweeping out area with one end at the pole and then the other end out there on the curve. I'm basically trying to find that area. Would you guys agree with me that for the entire time, the radial line's length is determined by that curve? So there's no switching like we had with the cardioid and the circle before. So I think what we can just do here for A is say that the area equals 1/2. Let's try that with a skinnier pen. Area equals 1/2 integral from 0 to pi. Yep, good. Of r squared. So that would be theta plus sine of 2 theta quantity squared d theta. Now once you have that set up, you got your 1/2, your r squared, your 0, and your pi. You just use Math 9. And did anybody take it all the way through to Math 9?
Yep.
What'd you get?
8.1? Oh, I didn't do the half.
Oh, okay, there we go. Perfect. So 4 point something? 382?
Yeah.
Okay, 4.382. And that'd be it. Number 2, as I walked around, I saw at least several of you had a really good start on B. There is something really weird about B that might take a little bit of a mind shift to get right. So this says find the angle theta that corresponds to the point on the curve with the x-coordinate -2. So I'm going to erase all my radial lines, and I'm going to try to point to this as best I can. So this would be that angle right there.
Wait, what if there's 2?
I think
Oh, it's only the
it's x equals -2. So we're talking about that right there. There's only one conceivable spot there. So are we not talking about this angle right there?
You know what I mean?
Does that make sense? So here's the setup that I saw a lot of you have. A lot of you had r cosine theta. So you had theta plus sine of 2 theta. There's r cosine theta, and you had equals negative 2. Isn't that essentially saying x equals negative 2?
Yep.
Okay. So a number of you get there, but then really it's like, what in the world do I do with that? Maybe did you explore on your calculator? When you're in radian mode, the whole intersect feature, not there, is it? It's not there.
That's so stressful.
So it is very stressful. I want to remind you all of something, though, and this is super duper important. What is it? Did you see it? You- Okay.
I was just kidding. I
So,
had an idea, but then I realized
This,
it's stupid.
this right here is just some equation. It's blah, blah, blah equals negative 2.
Oh, wait a minute.
So you just put that
You
in
can
there,
just hold on a minute.
So what can you do?
You can change it to
Cartesian.
lines.
You can change it to rectangular form and just use it to solve an equation. Now you know roughly what your angle should be. You've got to figure, kind of like Sam said, couldn't there be a lot of them? A lot of intersection points? There could be, because we got a sine and a cosine interacting here. But you know, don't you know for sure that your answer has to be between pi over 2 and pi? Based on our picture up there?
Yep.
Has to be between pi over 2 and pi. Or, there we go. I was doing it from my perspective. And so whatever answer you get, make sure that it fits. If I were you, I would just go back to rectangular form and graph whatever. Like you could add the 2 over and find an x-intercept, or you could graph both of those and find an intersection point, right? The way that we solve equations with your calculator. You could go either way there, to be honest.
Wait, I don't know how do you put it back in?
So just go use, like when you're in rectangular form, the input isn't theta, it's x's. This basically, the way I would read this is input plus sine of 2 input times cosine of input equals negative 2. And I don't care if the input's a theta or an x or a t or a y or a z or whatever you want to call it. I know in the end it's really a theta, but your calculator doesn't know, and your calculator doesn't care. It's just going to solve that equation.
Oh. So you're saying just do it for the sake of doing it?
Just solve the equation, and your calculator is going to say x equals, and in your mind you're thinking, well, really the variable's theta.
Okay.
The independent variable's theta. So then, like in our minds or on our papers, we'll just convert that back over to a theta just directly, right? Because the x is a theta. So the notation's funky because you got to go to rectangular form. But listen, all you're doing is you're solving that equation. And we're using your calculator to solve that equation. We know in the end the meaning of the answer is theta. Bless you.
Thank you.
Even though your calculator is going to say x equals.
So if you were to get, so like the answer is like 2.7, but obviously that's in radians, but how would you know if it was in radians? Like what if that was degrees? How do you know it's not degrees?
What mode are you in?
I mean, I'm in radian.
Yeah.
Oh, so it would be graphed differently. Okay, that makes sense.
Yep.
Silly Santi.
2.786. Okay.
Which is, in fact,
Because it has to be
between
between.
0 and pi.
Oh,
Oh.
It's between pi over 2 and pi, right? It's got to be in that second quadrant. I mean, we can tell from the picture. It's got to be in the second quadrant.
It's also within the range that it's supposed to be in, which is
So
always
because
a
negative 2 is on the other side, so.
Like when you
Okay.
do like 180 multiplied by 180 over pi, it's like one switches sides.
And then the degrees should still make sense. Yeah.
That makes sense.
Yep, I agree. Okay, so we're going to finish off with a couple of like explanation style questions, or at least one of them. Yeah, or yeah, C is a nice explanation question. I want to, if we do D or not, I'm not terribly concerned with that. I'm mostly concerned with doing C here today. We could even like throw D in tomorrow if we wanted to, or we could throw it in whenever we want. So let's take a look at C. C says for that domain, pi over 3 to 2 pi over 3, it says dr d theta is negative.
R is decreasing.
So, all right. So Santi says that means, so what does that say about R? Santi says R is decreasing. Oops. Does that all make sense to you guys? If the rate of change of the radius with respect to theta is negative, that means R is decreasing. What would be some other ways you could word that?
The distance is getting smaller.
There we go. So we'd say maybe distance between pole and curve is getting smaller.
If we said R is decreasing on like an MP exam, would
We're going to talk about that in a second. How else could you describe this? From the curve's perspective, the curve is,
Closing in.
that's the second part. It says, what does this fact say about the curve? So you say the curve is, you said?
Closing in.
Getting closer to
It's getting closer.
Yeah, there you go. You say the curve is getting closer to the pole. So let's talk about those first two. So the red one and the orange one. Which one is better, or are they basically just the same? I would actually favor the orange one, and here's why. So if you just said R is decreasing, if that's all you said, couldn't somebody say, oh, well, that means that R is negative. Now we have the picture, so we know this isn't true, but if all you said is R is decreasing, doesn't this still fit the narrative? R is negative and getting more negative. Right? And so that would actually mean the opposite, right? It's actually the curve, or you could say the radius is actually getting further from the origin, but that's not true. So if you wanted to say something like, instead of just saying R is decreasing, you could say like R is positive and R is decreasing. That actually is a little bit better picture of it, right? Because R is positive on that domain and R is also decreasing. And so that actually fits a little bit better narrative with the orange one. It's more equivalent by saying, hey, the distance there between the pole and the curve is getting smaller. I think they took, in this year, I think they did take R is decreasing. I'm just saying, if you want the red and the orange to kind of agree with each other, you have to say something about R being positive and R being decreasing. But I think those are some nice interpretations.
Is the last one?
So the last one is a finding of the maximum distance from the origin. And I think what I'm planning on doing here is over the course of the next week or so, if we have a spare 5 minutes, let's come back to that. Basically, it's a find a critical number, make a table, find the max R. So it's basically an issue of setting R prime equal to 0 and doing some trig. So not necessarily trivial, but I don't feel pressure to do it because it's not like this brand new thing. We've done a lot of maximizing over the years. So anyways, guys,
Years in the Aiden's
literally
semester.
years. For him, it's a semester, but yeah. Hope you guys have a great day. Tomorrow is going to be awesome. I'm so pumped to start series with you guys. I'm totally going to mess with you. Just foreshadowing. I'm going to absolutely mess with you tomorrow, and it's going to be so fun.
You're already messing.
But in a good way, in a good way. It really is.
You know, you say that because it's gonna